Welcome to the Deep Dive. In this episode, we will talk about Web Shepherd, advancing PRMs for reinforcing web agents. Okay, let's dive right into a challenge you probably face every day without thinking about it. Using the internet. Booking a ticket, ordering groceries, finding specific information across different sites, it feels pretty natural to
Yeah,
us.
second nature.
But imagine trying to build an AI agent to do these complex tasks for you. That's actually incredibly hard.
It really is. The web is vast, it's messy, constantly changing.
And it requires this long sequence of decisions, right, where one action depends on the last, and the whole environment shifts with every click. Current AI models, even the really powerful ones like multimodal large language models or MLLMs, they really struggle with this kind of long horizon sequential decision making needed for real web navigation.
Exactly. The core problem is guiding these agents, step by step. They need to make the right decision at each turn based on only a limited view of the website. And crucially, they need reliable feedback during the task, not just a thumbs up or down at the very end. That's often too late.
And that brings us to a significant gap this research highlights. In other AI fields like robotics or games, we have these specialized reward models that are great at providing that kind of step-by-step guidance.
Right. They've been around for a while.
But for the wild, unpredictable world of web navigation, dedicated process reward models, PRMs, they've been largely missing.
That's the gap. Instead, researchers have been trying to sort of force those big general-purpose MLLMs into the role of evaluators.
Which, as the paper points out, is proving prohibitively slow and, frankly, expensive.
Painfully slow and expensive. I mean, consider this detail from the paper.
Mm.
Just using GPT-4o for tree search on a benchmark called Web Arena cost around $14,000
Oh,
and took 40 hours on a single A100 GPU. That's just for the evaluation part, not even running the full agent.
that's unsustainable for practical use.
Totally. And their experiments also show that simply prompting MLLMs to act as evaluators actually performed worse than a specially trained model would. The need for a specialized, efficient solution was, well, pretty clear.
So, to tackle this head-on, this paper introduces Web Shepherd. It's presented as the first dedicated process reward model, a PRM designed specifically for these web navigation tasks.
And the distinction here between a PRM and an outcome reward model, or ORM, is really critical for the web. An ORM, it only tells you if you achieve the final goal, did you book the ticket, yes or no?
Right, the end state.
A PRM, however, evaluates the process. It looks at each individual step the agent takes. Did clicking that particular button actually move you closer to filtering the products correctly?
Why is getting feedback on the process so vital when you're interacting with a live website?
Because web actions often have real-world consequences you can't just easily undo.
Ah, okay. Like booking something non-refundable.
Exactly. If an agent is booking a flight, you don't want it to just keep retrying the final purchase because an ORM only says failure at the very end.
You'd run out of money fast.
You would. You need the agent to know, before it clicks, confirm if its previous steps were correct. Did it select the right dates? Did it input the passenger info correctly?
I see.
A PRM provides that fine-grained signal, evaluating decisions before they potentially become irreversible, which is essential for both reliable performance and, frankly, safety. It offers much richer feedback than just a simple binary success-failure.
Okay, so Web Shepherd is a PRM for the web. It evaluates the steps along the way. Our mission in this deep dive, then, is to understand how it works, look at the new resources they created to build and test it, and crucially, see what the experiments reveal about how well it actually performs and what potential it unlocks.
Sounds good. Let's unpack it.
All right. First, let's frame the problem of web navigation a bit more formally, as the paper does. They describe it as a partially observable Markov decision process, or POMDP. For our STEM-minded listeners, how would you simplify that concept?
Okay, well, think of a Markov decision process, an MDP, as a system where the future state only depends on the current state and the action taken, not the entire history of how you got there.
Right, the Markov property.
Exactly. Partially observable just means the agent doesn't have a complete, perfect picture of the environment state. On the web, the agent doesn't know the full website code or the database state behind it.
Mm-hmm.
It only sees what's presented to it at each step. Maybe the visual information from a screenshot and the structural and textual information from something called the accessibility tree. It has to make decisions based on this, well, limited view.
So it's navigating with partial information, trying to make the best guess at each step. What are the actions available to it in this model?
The actions are pretty intuitive. They're discrete browser commands. Things like click, I, where is an index referring to some interactive element on the page, like a button or a link,
Okay.
scrolling in a specific direction. Or type text, I, to input some text into a field identified by I.
And the paper highlights that despite these seemingly simple actions, current MLLM-based agents are often unreliable and prone to issues.
Yeah, very much so. They often get stuck in repetitive loops, just clicking the same thing over and over.
Oh.
Or they struggle to reason across the many steps required for a complex task, and generally aren't robust enough for anything beyond maybe the most straightforward interactions. Their performance tends to be brittle, is a good word for it.
Which brings us back to why just using those big MLLMs for evaluation isn't really cutting it. Beyond the cost we mentioned earlier, that $14,000 figure is just wow for evaluation alone.
Staggering.
The paper explicitly shows that prompting MLLMs to be evaluators performs worse than a model specifically trained for this exact task.
Precisely. And that's the motivation for Web Shepherd. It's not just another general-purpose model. It's designed from the ground up to excel at evaluating these web navigation trajectories right at the step level.
And a core, maybe even the cleverest innovation here, is the use of a structured checklist.
Absolutely. The checklist is foundational to Web Shepherd's whole approach. It lets you decompose a complex user instruction like, say, find a restaurant serving vegan options in London and make a reservation for 2 tomorrow night,
Okay, a multi-step goal.
into a sequence of smaller, checkable sub-goals.
Yeah.
Like step 1, navigate to restaurant search site. Step 2, search for restaurants in London. Then apply vegan filter, select a restaurant, find reservation option, input number of guests, input date, and finally, confirm reservation details.
And Web Shepherd leverages this checklist in 2 key ways, is that right?
That's right. First, given the user instruction, Web Shepherd can actually generate these task-specific checklists. It learns to do that. Second, and this is where the reward model function really comes in. At each step the agent takes, Web Shepherd assigns a reward based on how that action contributed to completing items on that generated checklist.
How does it quantify that contribution? How does it turn checklist progress into an actual reward score?
So the model is trained using a next token prediction objective. It learns to predict specific feedback tokens like yes, no, in progress, given the checklist, the current observation, what the agent sees, and the action it just took. For scoring, it uses something they call a verbalizer. Think of it like this. Instead of just spitting out a hard yes or no for whether a checklist item is complete, the model outputs probabilities for tokens like yes, no, and importantly, in progress.
Okay, so it's more nuanced.
Exactly. The verbalizer maps these probabilities, essentially, the model's confidence in each category, to a continuous score for that specific checklist item. The final reward for the step is then an average score across all the items on the checklist.
That in progress state seems really interesting. Why is knowing something is in progress more useful than just a binary yes-no?
It provides a much richer signal for guiding the agent. If an action results in an in-progress state for a checklist item, it tells the agent, okay, you're on the right track, but you need more actions to fully complete this sub-goal.
Got it.
For instance, maybe scrolling down a long page might put Find Reservation button into an in-progress state. This indicates the button is probably on the page somewhere, but it's not yet visible or clickable.
Right, a simple yes-no wouldn't capture that middle ground.
Exactly.
Yeah.
A binary score wouldn't give that nuance. This continuous fine-grained score is really essential for navigating complex, multi-step tasks effectively.
Now, building a specialized model like this requires specialized data, right? And the paper mentions the lack of existing training data for web navigation PRMs was a major obstacle.
It absolutely was. And overcoming that obstacle is actually a key contribution of this work, the creation of the Web PRM collection. This is presented as the first dataset specifically designed to train process reward models for web agents, providing exactly that step-by-step feedback signal that was missing.
What's inside this dataset? What does an entry look like?
Okay, so each entry contains the user instruction, the sequence of observations like screenshots and accessibility trees the agent would see at each step, the corresponding checklist for the task, the sequence of actions taken by a human expert to successfully complete the task,
Okay, the good path.
and crucially, a set of rejected actions. These are actions an agent might plausibly take at that step, but that are actually incorrect or suboptimal, examples of what not to do.
How did they collect all this? Was it fully automated or?
No, it involved human experts quite heavily. They were recruited and trained on using a specialized toolkit. The paper describes a graphical interface with predefined actions and a sidebar to track progress against the checklist in real time. These experts crafted complex instructions and then performed the tasks on live websites, recording their actions and the observations along the way. The raw data was then reviewed by other evaluators, and they filtered out invalid or ambiguous entries to make sure the quality was high.
And they even categorized the tasks by difficulty level: easy, medium, hard.
Yes, they did. And the data clearly reflects that difficulty. Easy tasks typically involved around 5 steps and maybe 3 or 4 checklist items.
Relatively simple.
Medium tasks were closer to 9 steps with 4 or 5 items. And the hard tasks can require over 20 steps. Interestingly, they often still had only 4 to 5 high-level checklist items, which suggests the difficulty comes more from the depth and complexity of the interaction needed for each step, rather than just having more distinct sub-goals.
That makes sense. What about the checklists themselves? Were those written by the human experts, too?
The checklists were primarily generated using GPT-4o, actually. It was given the instruction and the human expert's successful trajectory as input. And they specifically aimed for relatively coarse-grained items like apply filters, instead of listing out every single specific filter like filter by price, filter by brand.
Like coarse-grained.
To encourage the reward model to generalize better across different websites and slight variations in how a task might be executed, it makes the model more robust.
And the rejected actions, the examples of what not to do, how did they gather those?
They sampled incorrect actions from a variety of sources. Some came from the outputs of MLLMs like Qwen or other fine-tuned models that were attempting the tasks but failed.
So using failures from other models.
Right. Then they applied rule-based filtering and also human review to ensure these were genuinely bad or suboptimal actions, not just alternative valid ways to proceed down the path.
Okay.
The statistics in the paper interestingly show that rejected actions often involve proportionally more click actions compared to successful trajectories.
Suggesting that clicking on the wrong thing is a very common failure mode for these agents.
Seems likely, yeah.
So they built the model, Web Shepherd, and they built the necessary data, the Web PRM collection, and the checklist generation process. But they also needed a rigorous way to evaluate the reward model itself, separate from running a full, potentially expensive web agent.
Exactly. And that's where the Web Reward Bench comes in. This is introduced as the first meta-evaluation benchmark specifically designed for web navigation PRMs.
Meta-evaluation, meaning evaluating the evaluator.
Precisely. Its value is immense because testing the reward model directly is far more efficient, much faster and cheaper than building and running full agents guided by that model, which, as we discussed, can be very costly and time-consuming.
How is Web Reward Bench structured? How does it work?
It's built using instances taken from existing web navigation benchmarks, specifically Mind2Web and Web Arena, for a specific step within a task. It provides the agent's observation, what it sees, the relevant checklist for that task.
Yeah.
One chosen action, which is the correct action an expert would take.
The gold standard action.
And 4 rejected actions, which are suboptimal or incorrect alternatives. The reward model being tested is then evaluated on how well it scores the chosen action higher than those 4 rejected ones.
So it's like a multiple choice question for the reward model at each step?
Kind of, yeah. It needs to pick the best one out of 5 options based on its reward score. The benchmark includes 776 distinct step-level instances, which extends to 3,880 test instances when you consider all the action candidates, covering 220 different tasks.
And what metrics do they use to measure how well a PRM performs on this benchmark? You mentioned a few earlier.
Right. They use 3 key metrics. First, mean reciprocal rank, MRR. This measures how highly the preferred correct action is ranked among the 5 candidates by the reward model. A higher MRR means the correct action is consistently ranked near the top, ideally at rank 1.
Okay.
Second, step accuracy, AT step. This one's simpler. It's just the percentage of individual steps where the reward model assigns the absolute highest score to the preferred action among all 5 candidates.
Got it.
And third, trajectory accuracy, AC trash. This is the strictest and perhaps most telling metric. It measures the percentage of full trajectories, entire task sequences, where the preferred action was given the highest reward at every single step in that sequence.
Wow. Okay. That sounds really hard to achieve. One wrong step evaluation in a long sequence, and the whole trajectory counts as a failure for this metric.
Exactly. It indicates really robust and consistent step-level evaluation capability.
All right. So model, data, benchmark are all in place. Let's get to the juicy part. The experiments. What did they actually find when they tested Web Shepherd on Web Reward Bench? How did it stack up against using those general MLLMs as evaluators?
This is really where the breakthrough shows quite dramatically. The core finding is that existing MLLMs, even the really capable ones like GPT-4o, struggle significantly with assigning correct process rewards, especially on that challenging trajectory accuracy metric.
Can you give us some numbers to illustrate that gap?
Absolutely.
Yeah.
You'd look at Table 1 in the paper on the cross-domain test set. GPT-4o Mini, using both text and image input, even when given the guiding checklist, only manage a 5.0% trajectory accuracy.
5%? It's not great.
Not great at all for reliability. GPT-4o was slightly better, but still very low. Now, compare that to Web Shepherd 3b, the smaller version, using text plus image and the checklist. It achieved a stunning 65.0% trajectory accuracy on the exact same set.
Hold on, 65% compared to 5%. That's a massive difference.
It's huge. A 13x improvement in getting every single step right in a sequence. On step accuracy, Web Shepherd was also significantly better. The abstract mentions it's about 30 points higher than the GPT-4o baselines on the Web Arena portion of the benchmark.
Wow. Getting 65% of full trajectories evaluated correctly at every single step compared to 5% for a state-of-the-art MLLM isn't just an incremental improvement. That feels like a fundamental shift in capability for this specific task.
It really does. It underscores the value of building specialized models for specialized tasks like this.
Right. It's not just about scale, it's about architecture and training focus.
Exactly. And another significant takeaway from these Web Reward Bench experiments was the undeniable power of the checklist itself.
Yes, the guiding checklist.
Table 1 shows that providing a checklist significantly boosted performance for all the models they tested, including the MLLM baselines. It acts as essential guidance, helping the model understand the task's sub-goals and structure.
So the checklist helps everyone, but Web Shepherd leverages it much better.
Precisely. And the ablation studies they ran, shown in Figure 6, further reinforce this. They show that both the checklist and the specific feedback tokens Web Shepherd is trained to predict are critical for its performance. If you remove either one, the accuracy plummets.
What about multimodal input? We talked about text and image. You'd intuitively think using both would always be better, wouldn't you?
You would think so, but that was actually a surprising result, and consistent with some prior work they mentioned. While Web Shepherd performs well with multimodal input, text plus image, the experiments showed that for the MLLM baselines, adding image input didn't consistently help, and sometimes even hurt performance slightly, as seen in Table 1.
Huh. Any idea why?
The hypothesis is that processing multimodal web observations might introduce noise or ambiguity that these general MLLMs, perhaps not fine-tuned enough for this specific domain, struggle with. Maybe the visual information conflicts with the text, or just adds too much complexity.
Interesting. Okay, so Web Shepherd is vastly superior at predicting step-level rewards. That seems clear from the benchmark. But the million-dollar question, or maybe the $14,000 question,
Right.
is can this better reward signal actually guide an agent to perform web tasks more successfully in practice?
That's the crucial test, isn't it? They evaluated this using something called reward-guided trajectory search, specifically in a best-of-n setup.
Guest of unsearch. Okay, how does that work?
Here, they used a policy model, like GPT-4o Mini or the stronger GPT-4o, to generate several possible actions at each step of a task. Let's say it proposes 4 different clicks or scrolls.
Oh, okay, multiple options.
Then, they used the reward model, either an MLLM baseline or Web Shepherd, to evaluate each of those proposed actions and select the single best one according to its reward score. This setup directly tests if the reward model can effectively choose better steps and steer the agent towards success.
Makes sense. What did the results on Web Arena Lite, a standard benchmark for these agents, show for the actual task success rate? Did Web Shepherd guidance help?
It helps significantly. The results in Table 2 are quite compelling. So a base GPT-4o Mini policy without any reward guidance achieved a 23.64% success rate on the Web Arena Lite tasks.
Okay, about 1 in 4 tasks completed successfully.
Right. Now, when guided by GPT-4o Mini acting as a verifier, using the MLLM itself for guidance, the success rate barely budged. It went to 24.24%, almost no improvement.
So using the same MLLM for policy and verification didn't help much?
Not really. But when guided by Web Shepherd, even the smaller 3B version, the success rate jumped quite a bit, to 32.12%.
That's a noticeable jump.
And with a larger Web Shepherd AB model providing the guidance, the success rate reached 34.55%.
Hold on. So You start with a base GPT-4 mini policy getting 23.64% success. And just by using Web Shepherd 8B to pick the best action from its proposals, you boost that success rate to 34.55%.
That's right. A gain of over 10 percentage points.
And they point out something even more striking, that 34.55% achieved by the guided GPT-4 mini actually outperforms the stronger but unguided GPT-4 policy, which got 31.52% success on its own.
Exactly. That's a really key finding. You're taking a weaker base model GPT-4 mini, and simply by adding Web Shepherd's superior step-by-step guidance, you're making it perform better than a much stronger base model GPT-4 running without that guidance.
That's incredible. It really demonstrates the power of accurate process-level feedback. It's not just about having a smart agent, but about giving it the right signals along the way.
Precisely. It shows Web Shepherd provides a powerful guidance signal capable of significantly enhancing an agent's ability to navigate these complex web tasks, even if the underlying policy generation isn't top of the line.
And crucially, this performance boost comes with that massive cost advantage we keep mentioning.
Yes, Figure 1 and Table 10 really hammer this home. Web Shepherd 3B is approximately 10 times cheaper to run per evaluation than GPT-4ME, and a staggering 100 times cheaper than GPT-4.
100x cheaper for better guidance. That's pretty compelling.
That kind of efficiency is what could actually make these guided agents practical and deployable in the real world, not just research curiosities.
They also investigated the value of the detailed feedback Web Shepherd provides, not just the final reward score for ranking actions. You mentioned the in-progress state earlier. Did that kind of feedback prove useful?
Yes, it did. There was some prior research suggesting that this kind of explicit stepwise feedback might not actually help agents much, or could even be detrimental, maybe confusing the agent.
Oh, interesting.
But the experiments here, detailed in Table 3 and Table 7, showed the opposite for Web Shepherd. They set up an experiment where, if Web Shepherd predicted a drop in reward for the chosen action, they used its detailed feedback, like which checklist item wasn't progressing, to prompt the agent to rethink and refine its action.
So using the feedback for error correction?
Exactly. And this led to further performance improvements. A plus 3.03 percentage point boost in success rate for the 3B model, and plus 4.24 points for the 8B model, on top of the best of end games.
So the feedback is meaningful and actionable. It helps the agent identify and potentially recover from suboptimal moves.
That's what the results suggest, yes. Web Shepherd's feedback seems capable of pinpointing where things are going wrong.
Okay, moving into the discussion and analysis part of the paper. They dig into several factors behind these strong results. First, the quality of those generated checklists. How good were they?
They evaluated checklist quality using an LLM-based judging method called GEVAL. They found that the checklists generated, particularly those from a dedicated checklist model they trained specifically for this, were generally rated as high quality. That's in Table 11 and Figure 7.
And does better checklist quality lead to better rewards?
Yes, they found a positive correlation. Higher quality checklists generally led to better reward prediction accuracy from Web Shepherd. However, they also note that the model's own underlying capability sort of sets an upper bound. Even with a perfect checklist, the model needs to be able to interpret the state and action correctly.
Makes sense. They also compared different ways of actually training the reward model itself.
Right. They compared their generative reward modeling approach, training the model to predict those feedback tokens, yes, no, in progress, with the more traditional Bradley-Terry loss function.
Bradley-Terry. That's often used for training from pairwise preferences, like saying action A was better than action B.
Exactly. It's very common in RLHF, reinforcement learning from human feedback. But Figure 8 in the paper shows their generative approach significantly outperformed the model trained with Bradley-Terry loss, especially on out-of-distribution data like the Weberina subset of the benchmark.
Why the difference?
They suggest the Bradley-Terry loss model struggled to effectively incorporate the rich information contained in the checklist. It was less sensitive to the step-by-step task progress encoded there, making the generative approach, which directly models checklist completion, superior for this specific task.
And just revisiting that cost efficiency one more time to put a fine point on it with the actual numbers.
Sure. Table 10 lays it out very clearly. The estimated cost per 1,000 evaluation instances was $4.67 for Web Shepherd 3B.
Okay, under $5.
Compare that to $43.57 for GPT-4 Mini.
Nearly 10 times more.
And $435.74 for GPT-4.
Wow, almost 100 times more.
Yes. These orders of magnitude differences in cost are really the key to making sophisticated process reward models for complex web navigation feasible for real-world applications and, importantly, for large-scale training. like RLHF.
The case studies they include also offer some nice qualitative insights into why Web Shepherd works, showing what successful and unsuccessful trajectories look like from its reward perspective.
Right. Figure 9 is illustrative. It shows that successful trajectories tend to exhibit a smoother, more consistent increase in the predicted reward score over time. This reflects steady progress being made towards completing the checklist items.
And failures.
Failed trajectories often show flatter reward curves, or plateaus where the agent gets stuck, or even sudden drops. They also analyze common errors that lead to failure and lower reward scores.
Yeah.
You can find details in figures 15, 16, 17 in the appendix.
What kinds of errors?
Things like the agent misinterpreting the current state of the web page and taking repetitive, useless actions. Or failing to reason correctly about the future consequences of an action, for example, assigning a low reward to a necessary scroll action, because scrolling itself doesn't immediately complete a checklist item, even though it's needed to reveal the button that will.
Ah, the credit assignment problem.
Exactly. And another interesting failure mode was checklist hallucinations, where the agent or maybe the checklist generation process itself references elements or sections on the page that don't actually exist, leading to confusion.
So while the PRM, Web Shepherd, is great at evaluating the steps based on the checklist and observations, the underlying agent still needs to be able to interpret the visual and textual state reasonably well and propose sensible actions in the first place.
Absolutely. The PRM provides the crucial guidance signal, but the agent still needs a decent underlying policy for exploring the state space and interacting effectively with the web environment. Garbage in, garbage out still applies to some extent.
The paper also responsibly outlines some limitations of the current work and touches on potential societal impacts. What are some of the key limitations they mention?
In Appendix A, they note a few things. The current Web Shepherd version mainly focuses on text-based actions identified via the accessibility tree. It doesn't handle coordinate-based actions like clicking a specific pixel location, which are sometimes needed for complex interfaces.
Okay.
It also doesn't yet support multimodal instructions, like telling the agent, click on the image of the red chair. Applying Web Shepherd's reward signal for full end-to-end reinforcement learning is stated as future work.
So using it directly to train the agent policy from scratch, not just for search.
Right. And they also mentioned that the current models are still relatively small scale, the 3B and 8B parameter versions they studied. Scaling up could potentially yield further improvements.
And the potential impacts of this technology, both positive and negative.
On the positive side, as we've discussed throughout, Web Shepherd's capabilities could enable much more robust and general-purpose web agents. This could automate complex, goal-oriented tasks for everyone. And there are potential benefits for accessibility, too, helping users with disabilities navigate websites more easily, and generally improving the scalability and utility of digital assistants.
But like any powerful technology, especially one that can act autonomously on the internet, there are definitely risks involved.
Absolutely, and they acknowledge this clearly. The potential negative impacts discussed in the paper include the risk of agents performing harmful actions without explicit user consent.
Such as?
Things like submitting unauthorized forms, modifying sensitive data on accounts, or accessing restricted information, basically. Doing things online you wouldn't want an automated system doing without permission if the agent isn't properly constrained. There's also the risk of misalignment, which is a common concern in AI safety. This is where an agent might figure out how to exploit loopholes or unexpected behaviors in the web environment to get a high reward score from the PRM, without actually fulfilling the user's true underlying goal, gaming the system essentially.
Which really emphasizes the need for strong safety measures and careful design when deploying these kinds of agents.
Definitely. They stress the importance of implementing strict execution constraints, like only allowing actions on specific approved websites, robust permission controls, incorporating human oversight where necessary, especially for sensitive tasks, and having thorough auditing mechanisms to monitor agent behavior in any real-world application. Safety has to be paramount.
Okay, let's try to recap the key contributions here before we wrap up. What are the main takeaways?
Sure. I think there are three main contributions. First, the paper introduces Web Shepherd itself, which is the first dedicated process reward model specifically designed for web navigation, filling a pretty critical gap in the field.
Okay, the model.
Second, they provide two essential resources for the research community. The Web PRM collection, which is a novel dataset tailored for training these web PRMs.
Big data.
And third, Web Reward Bench, the first benchmark designed specifically for evaluating the reward models themselves efficiently and directly.
The benchmark. model data benchmark,
Hmm.
and the headline findings from their experiments using these.
The big headline is that Web Shepherd significantly outperforms general MLLMs in predicting step-level rewards for web navigation. It achieves dramatically higher accuracy, especially on that tough trajectory accuracy metric that requires getting every step right.
Right, the 65% meant you were a 5% difference was stark.
Exactly. And crucially,
Yeah.
when this superior reward signal is used to guide an agent via reward-guided search, like Best of N, it substantially boosts the agent's actual task success rates. Remember, it turned a weaker policy into one that outperformed a stronger MLLM baseline running alone.
And it did all this while being 10 to 100 times more cost efficient than using those MLLMs for the same evaluation purpose.
That cost efficiency point really can't be overstated for practical potential. And what's fascinating here is how broadly applicable this core idea, the checklist-based process reward model framework, might actually be.
Beyond just web navigation.
Potentially, yes. While this work focuses squarely on the web, the fundamental concept of breaking down a complex task into checkable subgoals and evaluating progress step by step, that could be really powerful in many other sequential decision-making domains.
Like where?
Anywhere you have sparse rewards, where the final outcome is hard to judge or comes too late, and where the environment is partially observable. Think maybe complex software usage, certain types of robotics tasks, maybe even scientific discovery processes. The checklist provides that intermediate structure and reward signal that's often missing.
That's a really interesting point about generalizability. So thinking about the power of these improving agents and the absolute importance of correctly evaluating their steps, as Web Shepherd aims to do, it leads to a bigger question, doesn't it? What does it really mean to ensure an AI agent's goals are truly aligned with our own, especially as they gain more autonomy and capability in complex, open-ended environments like the web?
It really highlights the ongoing and perhaps escalating challenge of building AI systems that are not just increasingly capable, but also fundamentally reliable, interpretable, and ultimately trustworthy enough to act safely and effectively on our behalf. It's not just about performance, but alignment and safety.
A fundamental question indeed. One that this kind of research pushes all of us to consider more deeply as the technology advances. Fascinating work.
Indeed. Lots to think about.